We have order logic, which is another kind of logic. That's a more powerful language that develops information about objects in a more compact way and also relationships between these objects. So, in this section, we will just discuss flavor of what this looks like. If you want to dive into this topic more, you can check more theory on books. So what is the syntax of first order logic? So now we have term that can be either constant symbols such as a, 10, or Columbia variables that are x, y, x, etc. And also you could use functions in terms of, for example, square root of x, sum of 1 and 2, etc. So we are going to make the language richer with constants, with variables, and with functions. So you could see already that instead of saying square 1 is clean, you could just use a variable to express any square. We are going to talk about atomic formulas and our predicates that apply to terms. For example, brother xy means that x is brother of y, or the element A is on both the element B. We are going to keep the same connectives, the conjunction, distinction, implication, double implication, and negation. We are going to be able to use equality, especially that we did with function as well. We are going to use what we call qualifiers, quantifiers, and these are very important to express information about all the objects or some of the objects. So the connectives, the equality, and the quantifiers can be applied to atomic formulas to create sentences in first order logic. You call FOL. So for instance, to express in first order logic that all squares are clean, we can write for all x if square of x then clean of x. This means that whenever there is an x that's a square, it is clean. To express the fact that there exist some dirty squares, we are going to use the quantifier exist. There exists x such that square of x and not clean of x, which means that there exist some squares that are not clean. How now can we express that some squares have chairs on top? So here are few examples using first order logic to express that. For example, all birds fly. You could write for all bird x then fly of x. To express that all birds fly, actually expect penguins. You could write for all x bird of x and not penguins of x then fly of x. If you would expect that every bird like candy, we are going to write this for all x kid of x then likes x candy. So candy in this case is a constant, and we have the likes, which is a pretty good with two arguments. The first one is the person or the kid, and the second one is the element that is liked. Some kids like candy, we have to write this as exist x kid of x and likes x candy. To express that brothers are siblings, we write that for all x and y, brother x and y means or implies that sibling x and y, so a more complicated one, one's mother is one's female. One's mother is a one's female parent. For all xy, mother of xy is if and only if female of X and parent X and Y. With first order logic, we can also do inference. While it is a little bit more complicated than propositional logic, there are procedures to do inference with knowledge base, first order logic formulas. So the aim is to try to reach natural language. So we have expressed different formulas in terms of propositional logic or order logic. The expressiveness of first order logic is powerful and suggests that it is possible to automate the conversion between natural language and logical expression. This is very variable for different applications, including personal assistants, question answering systems, and communicating with computers in general. That will put actually logical agents in the smart side of the intelligence level in our intelligence axis. To summarize, logical agents apply inference to knowledge base to drive new information and make decision. The basic concept of logic includes syntax, formal structure of sentences, cementing the truth of the sentences, entailment, the necessary truth of one sentence given another one. Inference is driving sentences from other sentences. Soundness is the derivation that produce only entailed sentences, and completeness, which derivations that can produce all entailed sentences. The Wampus word, as we have seen, requires the ability to represent partial and negated information, reasoned by cases, etc. Forward chaining are linear in time, complete for horn clauses. Resolution is complete for propositional logic as well. First order logic is a powerful way also to represent information and has proven actually to be sound and complete when we use the method that we were tried for first order logic. It is worth mentioning here that building logical agents was a main reason and research area in AI before the mid 90s. Logic is used in AI to represent the world but also to reason about the world. Logical agents has pros and cons. They are still used in some applications today, but the problem with logical agents is that they don't handle uncertainty. Hence, the use of probability more and more in AI, it is completely rule based, which means it does not use any kind of data to model the world, while learning addresses this point and uses data to make inventions or to make models. It is also how to model every aspect of the world so it can become very quickly, very overwhelming and tedious to write everything you know about the world. And there is no guarantee that you modeled everything. However, logical agents has a big advantage of being intelligible. The models produced are intelligible and it's possible to follow any proof using inference to know what's going on. How this inference was made by using these models that are encoded explicitly. So logical agents tend to disappear today, machine learning and probability based methods being more used today. However, I think that there is still beauty in them in terms of framework, the propositional logic, and first order logic frameworks are beautiful. And they actually have this intelligible feature that can be combined with other black box model that do provide explanation of the reason for prediction or inference.